Hey, welcome back, everyone. How's everyone doing? It's the fourth week of the semester, so um, keep moving forward. We are here today. Notice that's the last section in our text. We do have an appendix, the extreme value theorem, uh, but what we're finishing up today is sort of what we started on Friday in 15.3, looking at max and min. Uh, Optimization basically means find the maximum and minimum. But we're going to use a new technique today. So we pick up we'll pick up two new techniques related to what we were doing Thursday. We'll finish up a little bit from the maximum minima, the second derivative test, because we're going to use it for one of the methods here. And then Wednesday, we'll look at the extreme value theorem. And what's an extreme value? It's a big, either really big or really small. So it's a maximum or a minimum as well. The extreme value theorem gives us a way of finding if there is a maximum or a minimum. It's sort of an existence type thing. We'll take a look at that. And we've got Friday to finish up any content, maybe answer some questions. I'll do a little bit of start into the review, but it's kind of some space here uh, because you need to be thinking about finishing up all of this. Hopefully you've started into a few of the questions. It's okay if you left some behind, but you want to start finishing up that homework. Next week, we'll have 2 review days, and I'll have some activities for us to do here in class to try things out. So kind of like practice tests. We'll put a little bit of stress, but there's no grades involved, so maybe that's not as stressful, but it's going to get you ready for that test. And then this Friday in-class exam, it's paper and pencil. Um, I have not seen the actual exam yet, so but as I do, I'm sure it'll be early next week because we have to check it ourselves and give some feedback. So I'll let you know what that exam consists of. But we do have sort of a uh, an insight into the exam because we do have the in the review resources, and I encourage you to take a look at this. I'm just going to open it up here and take a quick look. These are review questions from the course administrators. What I have found is that, or course coordinators, I guess we call them, generally they're very close. Sometimes the coordinators take these questions as a template, change values a little bit, and that's your question for the exam. So they're taken out of the test bank and stuff. So you've hopefully see questions like we've done, like remember these rings are actually z values. So it's a 2-dimensional look at a 3-dimensional space. And then we get down into here. These are our, bisection. We were asked as, how are we going to test? Well, you may very well see graphs like this, and you have to be able to tell whether it's a max, a min, or a saddle point. Remember, what? X, Y, Z. Um, Actually, I don't think that's as, I don't think Q is a saddle point there. Do you agree with? No, it's kind of like on the slope. It's like nothing. Okay. Over here, Q is a saddle point, right? It goes down in one direction and sort of a max and a min at the same time. So you'll have pictures like that. And then they're going to have you use a second derivative test. So we're going to do a couple examples with that this morning of how we use a second derivative test, because we don't have a 3D graphing. Most of us don't. There is a calculator out there that will do 3D. And if you have it, you're welcome to use it. But most of us don't. So we're not going to rely on graphing it. We're going to use the second derivative test. And then as you come down here, we've got this. There's 2 methods for 15.4. We're going to look at substitution, which is really that second derivative test after one step. And then the Lagrange multipliers, Lagrange. I'm not sure which one. Somebody's name, they put it on there. It's a very specialized technique. the textbook does not give any insight to where it came from or why it works or anything. It's just, here it is, use it. And when do we use it? Whenever they say use a Lagrange multiplier, we'll use that technique, okay? But I was a little disappointed that there wasn't even any insight into why it worked or something, but that's okay. They says it's beyond their text. So I'm jumping into this updated slide deck. We're going to look at 15.4, constrained maximum and minimum. So for the last section, we were just looking all over for any maximum or minimum in a function. What we're going to do today is we're constraining it to some constraints, like we started off with in, I think, 6.1 and 2, right? There was some constraints, and then there was something we were trying to maximize or minimize. So similar to that, but now remember we're in 3 dimensions. So we'll have something that constrains it. What it means is it restricts the domain. The domain is not everywhere. It's just in this little space that they're constricting it to, okay? And so there's a new technique that we can say it's not necessarily a function maximum or minimum, except it is a function maximum minimum on that constraint. There might be bigger maximums elsewhere, minimums elsewhere, saddle points elsewhere, but in this restricted domain, we're looking for the largest and the smallest. Sometimes those will occur like on the edge, right? Remember we got those constraints, and where the 2 lines were crossing that point, those were our possible values, maximum or minimum. Okay, so first we're going to start off with a little bit of review from Friday that we kind of got stuck on, ran out of time on, and today's going to be a little bit shorter, but I'll make sure I keep moving forward. So we have second partial derivatives. So what is that? Well, we have some function, right? We take a first derivative. When we take a first partial derivative means there's more than one. So it's sort of like part of it. So there was this one, f of x of xy. And actually, we don't put the xy anymore. We just say this is one way of writing the partial with respect to x. And then we also had the partial with respect to y. Remember when we took the partial with respect to x, what did we do with y, or how did we think about y? Y was a constant, a number. So we just think, oh, y is 10, if you want to think. It could be any number, but it's a number. So typically, if it was just sitting there by itself, when you take a derivative of a constant, it's 0, right? Sometimes it tags along. But and then the other side, when we do y, the partial with respect to y, what did we do with x? Constant. Beautiful. Okay. Second step is we could take partial derivatives of the derivatives. So what does that look like? Let's kind of go. So this was a first derivative, and then we could do the partial derivative. And again, for each of these derivatives, there are 2 derivatives. And if we had 3 or 4 variables, there'd be 3 or 4. But the partial derivative, and we label it the partial derivative of x, of f of x, right? Of x that we took. And then the second letter tells us what's the other variable we're taking the derivative of. So we take the first derivative with respect to x, and we're going to take it with respect to x again. But the second time, or the other variable, is we take the derivative with respect to x, the first derivative with respect to x, but then the second is with respect to y. Okay, so it's the same process. It's just we're starting at a different level. So we're just taking a derivative. You could think of these as, whatever. And then over on the y, so these are second derivatives, we could take the second derivative of y with respect to x, or we could take the second derivative of y with respect to y. And does anyone remember, we did an example, what ends up happening with these 2 in the middle here? They're the same. So it saves us some work. We could just do one. You could do both. It's kind of a good way to check, but they need to be equal. So these 2 in the middle are going to be equal. Okay, so that's the whole concept. And again, we use that in the 15.3 homework. There's 2 questions that we're going to do some second derivatives on. And then today we'll also use it on max and mins, and and we can use this second derivative test back in 15.3 as well. Okay, questions about that? That's our little diagram. Okay, let's see. So the second derivative test, we take those values. So this is your f of xx, f of yy. Notice they're being multiplied. So maybe just in shorthand. And we're taking them, we're plugging in the critical points. So let's think back. How do we find a critical point? Critical point is anywhere the first derivative equals 0. Good. So we set that. So there's a couple steps we'll do in here, but first derivative equals 0 gives us a critical point. It may or may not be a max or a min. It could be a saddle point. We're going to find, but this test will tell us what kind of point it is, possibly. And then notice here, xy, since they're the same, you multiply them or you just square them. So we've got these two multiplied, and then we subtract the middle one squared. So you multiply the two that are the same, you multiply the two that are different, xy and yx, okay, and you subtract the two, and that gives you some kind of a number. The number itself is not, it doesn't matter. What matters is it positive, negative, or 0? Okay. It's called a Hessian. Who cares? We'll just call it H, right? I'd give it a different name. I don't know. If it's positive, then the two things could happen. So if this is a positive number, then we look to the second derivative of x with respect to x. If that's greater than 0, then we've got a minimum. And if it is less than 0, if it's negative, so this is not h, h is positive. If the second derivative of x with respect to x is negative, so we're just looking at this little part here, that's negative, then we've got a maximum. Okay, so that tells us everything we need to know. If h is negative, then we've got a saddle point. But if it equals 0, then we throw the whole test away because it didn't tell us anything. It's inconclusive. Then we got to go to the graph. Again, if we're on a test and we end up with 0, probably an error because we aren't going to be able to go to a graph. Okay, so we will have you on you'll see the practice test questions. They'll say use the second derivative test. This is the second derivative test. So you want to maybe scheme this out somehow on a note card. I don't know if it'll be provided or not. As we do review, we'll get there. Don't worry so much about it. My goal is, the way I studied is I'd make like a 4x6 card. So it was hard. And I'd put things like this on there because when I'm doing my homework, I'm going to need to go back to it. And I didn't want to, back in the day when we had books, right? I didn't want to flip back and forth in it. We got books, but you got to go into online. But those cards would be there. And what I found is as I did my homework, I would look at it. When I do my homework, I'd write it. I'd rewrite it. And over time, I would just remember it without having to sit there and say, I got to memorize this for a test, right? Stress, and it never worked. But if you just sort of look at it, eventually it's there. Okay, you'll find it. So I encourage you to do something along that line. Could be a piece of whatever works for you, but important things like this that we use over and over again, have on a little card that's ready to use. And even though we're putting your answers into a computer, while you could do things in your head, you can also, it's good to write it down so that you can go back, or put it on a tablet so that you can go back and review your work. Okay. Any questions on this? Okay, so we're just going to see how to do it. Same thing we're going to do with the next thing on Lagrange multipliers. We'll show you what it is, and then we'll just use it. Why does this work? I don't know. It just does. Okay. Somebody spent probably their lifetime researching it, getting their doctorate in this field or something. I believe them. Okay. It's been tested out. Okay. So let's take this one. We were working with this one on Friday. So if you go back in your notes, I think we took at least the first derivative. We found the critical points. And maybe we even did the second derivative on it. I'm not sure. But anyway, we'll take the first derivative. So the goal is we want to find maximum and minimums here. So first thing we need to do is find critical points. So we'll kind of go through the steps. So I'll go over here, f of xx, and that's going to be, oh, no. Can't take the second derivative before you take the first, right? Oops. Get rid of that. Come on, there we go. Okay, first derivative with respect to x. So x squared, its derivative is 2x. Remember, y is a constant. If it was like a number 3, it just tags along, right? So we don't take its derivative. 2x to the first power times y. In the middle, we have minus 2x, or minus x squared, which becomes minus 2x when we take its derivative. And then when we take the derivative of 2y squared, since y is a constant, that is 0. I'll put that minus 0. So we took the derivative of each term with respect to x. Y just is a constant, so if it was multiplied, it just tags along. No product rule here. Come over here. Let's do the same thing. Let's take the derivative with respect to y. X squared y. Now this time when we take the derivative of y, we get 1. So the x squared times 1. In the middle, we've got minus x squared. X is a constant, so that's a 0. And then finally, we got minus 2x squared. And so when we take that derivative, 2 times 2 is 4. It becomes y to the first power. We okay so far? Let's give us a little bit of review. To find the critical points, what do? Set these equal to 0. Okay. So I take 2xy minus 2x equals 0. And I think I remember, I had some extraneous points. I think there was maybe a constraint like x was greater than 0 or something like that. Anyway, we'll get there. So 2x, let's factor that out. That gives us y minus 1 equals 0. So either 2x equals 0 or y minus 1 equals 0. So that gave us either x equals 0 or y equaled 1. When we come over here, we get x squared minus 4y equals 0. And I think the problem is we have to check that both of these have to be true. If you put in 0 for x, y would have to be 0, right? No real way to solve this, but we can plug in the values for x. So we put in 0 for x. We get that divided by negative 4, that y would be equal to 0. So we've got a critical point at 0, 0. We could put in y equal 1. That gives us x squared minus 4 times 1 equals 0. X squared equals 4, adding 4 to both sides. So x equals, take the square root of both sides, plus or minus 2. Okay, so we got that one when x was equal to, or when y was equal to 1. So that gives us 2 critical points. 2, 1, and minus 2, 1. I think what I did is I also combined 0 and 2, and I shouldn't, because x can't be 0 and 2 at the same time. And I may have combined 2 and 1, I think, and I wasn't getting a max or min. If x is 2, y can't be 1. Whereas can it? Actually, that would give you 4. Actually, it can, yeah. I think I combined 2 and 0. If x is 2, y can't be 0, because that would give you 4 minus 0 equals 0, which gives you 4 equals 0. So I think I forgot to check back into one of my functions at that point that I was using isn't going to work. Okay, so these are our critical points. And we're going to use the second derivative test now to see which are maximums and minimums. Again, when we did this question, we looked at the graph, and then we looked at a table of x and y values, and we saw when we went up, or I think one's a saddle point, one was a max, maybe. I think we got two maxes or two mins. Anyway, we'll figure it out again. We're going to use the Hessian. Okay, what is the Hessian? Well, now we need to find the second derivatives. Is it okay if I take off this work here? It's in the video. Yes.
By the 0 minus 4y, okay, so y becomes 0 because is that why your y is equal to 0 to the right?
Yes.
So we got that right?
Yes. So over here, I figured out that x equals 0 is a solution over here. So if I plug that in over here, let's admit, okay, x is, because these are related, right? If x is 0, then you get minus 4y equals 0. The only way that could be 0 is if y equals 0. They divide both sides by negative 4.
Why did you switch from 1?
Well, then I also found that y was equal to 1. So I want to say, okay, if y is equal to 1, what would x be? So y equals 1 as a solution. So that gives us x squared minus 4. So I added 4 to both sides. I skipped that step. Okay, and then I take the square root of both sides, and I got that x could be plus or minus 2 when y is 1. So these guys go together, 1 and plus or minus 2. So that gives us 2 points. And for y equals 0, I used x equals 0. So when x is 0, y is 0. So those two go together. So yeah, I was able to sort of, and it'll always happen. You'll be able to solve one side for x and y maybe, and then you use that on the other side, plugging those in, see which kind of solutions you get. Does that make sense? Kind of a little bit of practice. Okay, so now let me go ahead and erase that part. Again, you can always go back or take a screenshot. It's a video. I am recording, aren't I? Hopefully. Yes, I am. I forget sometimes. I've gotten so used to it. Because what I want to do is I want to just use the same page. And we're going to take the second derivative. We're going to figure out what the Hessian is. And actually, it's not too bad of a word once you get used to it. It's kind of cool. So I guess I'll use it. Okay, so now let's do that in red. We're going to come here, and remember there are two partials, second partials of the first partial. Okay, so we'll take the derivative of x, that first derivative with respect to x. So we're using this as our function. So x, take its derivative, that's 1. So we're left with 2y. And then minus 2x, when we take this derivative, we have minus 2. That's fx with respect to x. Then when we take the derivative of x with respect to y, first part, derivative of y is 1, so we're left with 2x. Derivative of 2x is a constant, so that is 0. And we're going to verify that over here when we take the derivative of y with respect to x. So I take that so that those two are supposed to be equal, right? Let's test it out. So this is the derivative of y with respect to x. So we're taking the derivative of x. So this gives us here x squared becomes 2x. 0 remains 0. And derivative of 4y is 0 because y is a constant. We're doing this. 2x is 2x. Okay, good. These guys check out. They're the same. They're supposed to be the same. And then I take the derivative of y with respect to y. So I come here, x squared is a constant, 0, 0. And then I take the derivative of negative 4y. I just get negative 4. We good so far? That's the second derivative. It's not the second derivative test quite yet, but that is our second derivative. Second derivative test says we're going to find something called h. And we'll take f of x at a critical point, at a point, And we're going to multiply that by f of y at that point. And notice f of y is always going to be negative 4, so it doesn't really matter what point we use, but that's good. And then we're going to subtract f of xy at that point squared. Okay. So what we have, let's do this. H is going to be equal to 2y minus 2 times negative 4 minus 2x squared. And we need to test it at each of these 3 points, because what we're doing is this test is going to tell us which kind of a max or min, well, if it's a maximum, minimum, or a saddle point. It's going to tell us what kind of point it is, hopefully. If it equals 0, then it doesn't tell us anything. Okay, so let's test out 0, 0. That's probably the easiest one to test, right? Both x and y are 0, so the Hessian, I'll do it this way. I don't know if this is their notation, but we'll make it up. Plug in 0 for y. 2 times 0 is 0, so we have a minus 2 times minus 4, because there's nothing to plug in there. Plug in 0 for x. 0 times 2 is 0. 0 squared is 0, so minus 0. So this gives us a Hessian of negative 2 times negative 4. It gives us positive 6. And I'm going to emphasize that with a plus sign. Does it matter that it's 6? No, it just matters that it is a positive number. So what does this mean for the point 0, 0? Fortunately, I can just go back. The Hessian was positive. So now what do we need to look at? We need to look at f of x. If it's positive, if the fxx is positive, then we've got a minimum. If it's negative, we've got a maximum. Yes. What's that? Oh yeah, it would. That's why it doesn't matter as I put 6. I added them instead of multiplied. We do that all the time though. But that's what I like about math. Sometimes you can make some mistakes and it doesn't really matter. But let's fix that. Except like you're on a job interview for a teaching position, you make a kind of sometimes that. Good. Anyone else recognize that was 8? Or did you think that there's some new math out there where, okay, so yeah, 2 times 4 is 8. Okay. Okay, but it's positive. So now we look at this one, right? This is the f. Is that positive or negative? That's negative. What do we have? That's why I need my card. It's negative, which means it's less than 0, which means we have a maximum in that case. So this is a max. Okay, and I think we found that when we looked at the graph that was also a max. So multiple ways to do it, but here's a second derivative test because we're not going to have access to a 3D graphing, right? We check the other 2 points. Wow, time goes fast. And so 2, 1, we plug that in. 2 is x and 1 is y. So when y is 1, we get 2 minus 2. That's going to give us 0 times negative 4. So that's still 0. Minus, we plug in 2 for x. 2 times 2 is 4. 4 squared is 16. That's negative 16. That's right so far, isn't it? Yeah, 2 times 2 is 4. 4 squared is 16. We get a negative 16, so the Hessian is negative. What does that tell us? A negative Hessian tells us we have a saddle point. And I believe that's what we had. We had like this, and then we had 2 saddle. I think we're going to get 2 saddle points out of this. But notice how I've had to go back and forth. If I do this with my homework enough, eventually it'll sink in. It might be provided with the exam. I can't tell you yes or no, but I'll find that out before next week as much as I can. Okay, and then you put in the negative 2, 1, and I think you'll see that, see 1, we still get 0 here, so we get 0 times negative 4. And then we get minus, plugging in negative 2, that gives us negative 4, but when you square it, you still get positive 16. So we get a negative value. And so this also is a saddle point. And again, go back and review what we did on Friday. You'll see we get the same answers, but here's a different way of doing it with the second derivative test. And for the exam, that's what they're going to ask you, use the second derivative test. So far, so good. Okay. I'm going to save myself a little bit of time. There's this thing called the substitution method. So this is the new section. So this is 14.4. And this is going to be not just the minimum and maximum of a function, but of a function subject to some kind of a constraint. We're going to limit the domain. So it might not be absolute, or, anyway, it's got a constraint. I'm going to get this one set up. We won't work all the way through it because basically we would do all the same steps we just did with the substitution method. And in the homework, there are none with the substitution method. This is from the practice test, though, so I thought maybe I better at least mention the substitution method, and I'll see if there's going to be one on the test or not. There are none in the homework, okay? So we don't have to worry about doing these right away. But basically, substitution method, you take the constraint, solve it for one of the variables, which is nice because this has already been done for us, right? Z equals 5y. We plug it back into the original function, and again, they're giving us a function with 3 variables. None of the homework has 3 variables. They all just do x and y. But what we're going to see is when we plug in z equals 5y, so we're going to replace z squared with 5y, we really get a function that has only 2 variables. So we get 1 minus x squared minus y squared. Z squared is going to become minus 5y squared. So that becomes 1 minus x squared minus y squared. This becomes minus 25y squared. So looks like we get 1 minus x squared minus 26y squared. And I'll do a video on this because it is in my goal is, at least over this next week or the weekend, to make videos of all the practice test questions in case you need them. Okay, so we'll work through that. So then what we would do is we would do the same thing of finding critical points, and then once we had the critical points, we would take the second derivative so we could use the second derivative test. Okay, so same process we just did with a different thing, and that's how substitution works. You take the constraint, solve it for one of the variables, plug it in, and there we go. Again, there's only one on the whole practice test. There is none in the homework that have you doing it. I was going to skip it, but then I looked at the practice test. I said, well, watch them put one of these on the test. So it may or may not be there, but it's really just has one more step, do the substitution, and then it's just like the previous one we did. Okay, I want to get into the next subtopic, which is the Lagrange multiplier. Lagrange. I think he's French, so that's maybe it's more Lagrange, but please forgive me on my pronunciation. This is when it's difficult or impossible to solve. Sometimes we might have like x squared plus y squared equals that, and it's really difficult to solve for one of the variables, or you get multiple things. It makes it really complicated. We can use something called a Lagrange multiplier. It's a simple thing. It's a created thing. Somebody probably did their doctoral work, or at least did their life research on this, figured it worked, showed it to the community. Oh, this works. We don't care why. It just does. Maybe we do care, maybe we don't. But it works. In our text, they're not going to tell us why it works or explain it. They just say it works, so use it. And what is a Lagrange multiplier? Well, we've got some some function, f of x, y, and we've got a constraint. What we do is we set whatever the constraint is, we get it all to one side so it'll be equal to 0. And that's where whatever's on the left-hand side, that's what we're going to call g of x. And then we get this little funky formula. Why do we get it? because somebody figured out it works. Okay, that's all we're doing. We take the f of x function, the function we're given, we're trying to find its maximum or minimum, minus some multiplier. That's the, and it's a Greek L for Lagrange, I guess, Lagrange. It's a number, but you're going to see we usually don't care what that number is. It's just that there is some number that we multiply it that this is something of value. But usually we don't have to find what that number is. It's going to cancel out somehow. That's the hope. I think it mostly does. We don't really need it. But when we do this thing, what this gives us is a function where we can, see if I remember what we do with this, where we take the first derivative, the first partial derivative with x, first partial derivative with y, and the constraint, and we're able to solve that system of equations. Okay. Oh, the candidates for the relative extreme occur at the critical points, L of x. Find them, set the partial derivatives, and notice it could be more than two unknowns, but we're only going to do it two. Find the set of all partial derivatives of Lx. Okay, we do that. Set them equal to 0. Solve the resulting system together with the constraint for the unknowns, x and y. You can solve it for Lagrange, but we don't, again, we usually don't care because we're looking for the critical points. The points x, y that occur in these solutions are then the candidates for the relative extrema. And then when we plug them back into the original function, f of x, we see which one's the biggest or which one's the smallest. We don't have to do a second derivative test. In the book, they tell you the second derivative test is not, this function doesn't do well under the second derivative test. So it doesn't really apply here. So all we're doing is we use this to find critical point candidates. We plug them in here. The biggest one is a max. The smallest one is a min, subject to those constraints. It doesn't really help us with saddle points, but that's what it'll give us, okay? And typically with constraints, you've got like a ring or something, so probably less likely to get saddle points. Okay, let's look at an example, because that's really all we ought to do is be able to do it. This down. Okay, we have a very simple function, 2xy. And you might recognize that that could, like x and y, x times y, this could be a area function, right? We don't know what it is, but there's some questions in the book that will have you like building a fence and it encloses an area. That's kind of what you're going to be working with. X times y is the area function, okay? We're subject to this constraint. I can't remember. Let's see if I go there. Yeah. So the first thing we do is we're going to rewrite the constraint equal to 0. So we subtract 32 from both sides. 32. And so we get that g of x, y, that this function is x squared plus 4y squared minus 32. That's equal to 0. Okay. So that's the function we're going to use in our formula. That's the function we're going to use at the beginning. And I think I copied over the Lagrange. So the goal is to maximize 2xy subject to this as our constraint. So g of xy, that's our Lagrangian function. Come up with this stuff. So we want to put it into this. Okay, so this is our Lagrange multiplier formula. It's just first one minus the second one times some kind of number. So we put in f of xy. That's going to be, let's change colors here. That's going to be 2xy. This is L of xy. So we're just creating a new function that works. There's some lambda times x squared plus 4y squared minus 32. So L of xy is equal to 2xy minus lambda x squared plus 4 lambda y squared minus 32 lambda. And again, lambda is a multiplier. It is a number. It's some kind of constant. It's just saying there is one that exists. Sometimes you can figure out what it is that would make it work. Again, our goal is to find maximums and minimums, not necessarily that multiplier. So far, we good? Okay, this is just a given. This is what we use. We don't know why. They just told us it works. So we do that. Gives us a function now, though we can, it's as simplified as we can get. What do we do with this function? I think we go to the next page. Let me see. Oops. Yeah, I go to the next page. Is what we've got. Except I don't think yeah. I have to do this. Okay, we do two things. We find, not f, we find the partial with respect to x of this function. Okay, so 2xy, take the derivative of x, what are we left with? 2y. Take the derivative of x, lambda x squared, we get minus 2 lambda x to the first power. We take the derivative of y squared lambda 4. Those are all constants. That's going to be a derivative of 0. I'll put that there just as a placeholder. And then we take the derivative of negative 32 lambda, which is a constant. That's also 0. So notice we have a nice simple little function for L of xx, or L of x. And again, what we do is we take 2y minus 2 lambda x, and we set that equal to 0. Okay. But the other one we're going to do, before we go too far, because we got both an x and a y in there, let's see when we take L with respect to y. See what function we get. Okay, 2xy, we take that derivative. Derivative of y is 1. We get 2x. Derivative of lambda x squared is 0 because x is a constant. Derivative of 4 lambda y squared is going to be plus, the 2 comes down. 2 times 4 is 8. Thanks for correcting me on that. I don't want to get it. Yes, sir. Here? I have it as plus 4y squared. Oh, thank you. Thank you. There. Okay. So that goes through and making that a plus. Okay. Thank you. Minus 8 comes down lambda y. Okay. And then the 32 is a constant. So we set this equal to 0. 2x minus 8 lambda y equals 0. So that's another function. And then we also have the constraint, and the constraint was this function here. So then we also have x squared plus 4y squared minus 32. I guess it's right up there, but that also equals 0. And then we have to simultaneously, I got about 5 minutes, so we'll finish up on this. We have to simultaneously solve these for x and y value that works. One thing to do is solve one of the equations for x or y, substitute it into the other one, and then we could solve and then solve back and see which ones work. So let's take this one. I'm going to add 2 lambda x to both sides. So I get 2y equals 2 lambda x. Did I get that? Wait, this is a negative. Oh, I did that part there. I just, okay. And then we divide both sides by 2. We get y equals lambda x. Okay. Just remember, in the way they solved this, they ended up with x over y. So far, so good. So then we could take this other one over here, and we can plug in for y, we can plug in lambda x. So we get 2x minus 8 lambda times lambda x equals 0. 2x minus 8x lambda squared equals 0. You can it's going to give us x equals 0. Which you go through and x is not equal to, let's see, what did I, I did something wrong here. I don't remember what it was. I know, let's do this. I'm going to have to come back. It must, one of these is supposed to solve for like x over y. Well, now I'm stressed and I can't think of what it's supposed to work. We'll follow up with this, but the method is, I'm doing the method right, but I did something wrong here, which I can't see what it is because I know in the solution they end up with x over y, and they substitute that. So we'll work at it. You can go to the original PowerPoint. They have worked it through. This is the same one from the text, but I'll do this, and by Wednesday we'll have that up and running. Sorry about that. It happens though, right? During my office hours, I realized my error. It was just a rookie error. First time teaching this class. What we want to do is we want to solve for lambda, not for y. Not that it wouldn't have worked, but it wasn't being real helpful for us. So what I'll do here is I'll divide by 2x, giving us that lambda equals y over x. If I make that substitution, then I get some help. So I want to erase this part. Let's start over here. And we're going to substitute this in for lambda here. So we get 2x minus 8 y over x, y equals 0. It's not a beautiful thing to work with, but we can make do. So we get 2x minus 8y squared over x equals 0. We can subtract 2x from both sides. I'm running out of space here, but so let me do this. I'm going to put the result up at the top to give myself some more room. So that gives us negative 8y squared over x equals negative 2x. Multiply both sides by negative x. Gives us 8y squared equals 2x squared. Okay. Now we can use our constraint. That's where I was going. I said, what are we going next? So we have 8y squared. We have a 4y squared. So we could write this as 2 times 4y squared equals 2x squared. Divide both sides by 2. Sorry about this all. And so that's going to give us 4y squared equals x squared. That we can substitute into the constraint function, which gives us x squared, 4y squared equals x squared. So that's plus, just make sure I got that. Yeah, the constraint is correct. Plus x squared minus 32 equals 0. That gives us 2x squared. Add 32 to both sides. Divide by 2. You get x squared equals 16. Take the square root, and you get that x equals plus or minus 4. Okay. Then we can take this 4, x equals 4, and we can plug it back into this equation here. Again, wait, that's where we solved it. We plugged it into the constraint. Well, you could plug it anywhere, and you can then solve for y. Okay, this is a little bit of a mess, but I just wanted to show you we could go forward. I'll do this on like a Word doc where I have more room to bring it down, but that was the error. Solve for lambda, replace that, and then you get your x and your y's. And then the next step is to use this system, plug in for any of these other ones, probably down here, plug in for x, and then you could solve for y. I think you get 2 values for y as well, because y squared, and then you get 4 particular points. And then from there, you plug those back into the original function. And the original function's right here. and figure out which ones give you the max and min. I think 2 of them will give you either a max or a min, the same value. So give that a try. I'll go back and work this one from step 1 again, but just wanted to make this a part of the recorded lesson.